Hello, everyone. This is going to be very different, I guess, from the other stuff you've seen. So this is joint work with Pranav, who was doing a master's degree at the University of Cambridge. Unfortunately, he couldn't make it due to visa restrictions. And then I guess this is one of my last papers with Ross, who unfortunately recently passed away. And for those who couldn't tell, Pranav is the person in the middle, just between the dogs, just there. And the gentleman is looking for a PhD placement. So if you're looking for a candidate, I think he will be a good one. All right, so I'm not sure if many of you remember the times where every now and then your computer would stop and tell you, you really need to move your mouse. And when you do move your mouse, this is done to help with some entropy. And nowadays, I don't really see this much. I'm not sure why. Maybe we don't need that much entropy. But let's imagine we move this mouse and we have some sort of a cryptographic application running in the back, and it gives us this random-looking string, so just a bunch of zeros and ones. So what do people think? Does this look random to you? Do people have ideas? Yes? No? Do you want to raise a hand if you think it is? Yes, it looks relatively random. So what if I highlight these ones, these numbers? Does that still look random to you? And the answer is, it's still the same string. It's actually quite random. But you see some sort of structures, and you start questioning your own logic. And the thing about randomness is that it's extremely fundamental to everything we do. And if you go back a good couple of decades, you'll find plenty of literature in cryptography that discuss randomness quite explicitly. And there was a lot of work on defining properties we expect out of crypto systems. In part because randomness is pretty much fundamental to everything in crypto. So the usual setup is we have a little bit of randomness. This is this dice, and then you sample some sort of a key from it, and then the other side also does it, and then you perform some magic, and here you go. You have established a secure channel, and adversaries can't do much. And then what people figured out is that in many ways, because randomness defines all of this basic backbone of cryptography, if you are capable of replacing this randomness with something else, with this some sort of deterministic randomness, then you can actually quite predictably tell what sort of numbers are going to be sampled from it, and then if those things are used as keys, then you can break the cryptographic protocol, some of them, out of the systems, and then perhaps spy on the communications. So at this point, you may think, Ilia, this is made up. Of course, nothing like this happens. And as a matter of fact, it does. We have known instances of explicitly where this happens, and some sort of less known, but kind of assumed to be true. And if you're interested, read up on some Edward Snowden leaked documents on backdoor randomness and computers supplied to some states. So long story short, we have seen adversaries use this vector, allegedly. Importantly, because it's such an important part of cryptography, there are standards and standardized ways to perform constructions where people generally agree that this is a good way to construct those pseudorandom number generators. And they always come with tests. So namely, you can do your own construction, plug in a bunch of tests, test whether a given random sequence appears random. And again, because it's a relatively vague definition, and definition of randomness generally is quite vague, it's very hard to tell how random a sequence is. It's all relatively random. They often fail. And importantly, there are also additional constraints on top of sample size, because if you have a very long random sequence, you may discover that actually estimating how random it is will take a significant amount of time. And usually, if you take the classical NIST standards, it will take hours to run them, even on modern hardware. Let's not talk about what happened in the past. And the important takeaway here is we kind of know how to do this with crypto. And what we know from there is that it's really far from perfect. And as a matter of fact, a lot of pseudorandom number generators, or PRNGs, that we rely on today fail some of the randomness tests. And we kind of still say, OK, they're good enough for applications we want. And if you're interested in what sort of phrasing that NIST uses, this is the standards body, you'll discover that often it says, well, you should test at least maybe 100,000 sequences. But if you have specific applications with specific significance, maybe ideally you want to check more. But you make a decision. And at the same time, randomness in machine learning is also quite fundamental. And so, for example, stochastic gradients and the random version of gradient descent relies on sampling uniform noise. And at the same time, we have a lot of other applications where sampling a lot of random noise is quite fundamental in making sure that the decisions we get out of our models are interpretable and meaningful and robust. And an example here would be uncertainty estimation. It's as fundamental as it goes in machine learning. And any sort of Monte Carlian methods we rely on here explicitly say we need noise. It's very parametric noise because otherwise none of the proofs work. At the same time, because most of the standards for PRNGs actually come from the cryptographic world, they are designed for a very different sort of purposes. And importantly, there are three main differences. So in crypto, we care about mostly uniform noise and all of the constructions, and especially hardware components that we usually build. We calibrate explicitly for uniform noise, whereas in machine learning, thanks to CLT, the central limit theorem, and a lot of mathematical reasons, it's really pleasant to work with Gaussian noise. And it's quite commonly, we also rely on other sort of power families, like Laplace noise. And nobody explicitly tests for this at all. At the same time, in cryptography, we usually sample very small amount of noise. We don't really care about gigabytes of data. Very often, like 1,000 bytes is more than enough for most of the applications. Whereas in ML, if you really want to compute uncertainty with respect to some sort of an input, and you expect that your model takes in something like a 32-bit float, you'll discover that you need to sample quite a lot in order to get any sort of meaningful result out of this. And this also comes with an additional complexity. Latency is a big requirement. It's OK to stop and move and wiggle the mouse very so slightly if you're sampling a couple of bytes. But if you need for every single image to be classified correctly an estimated confidence bound to move your mouse, you may discover that most of the time you're going to be spending moving your mouse. And obviously, this is not really acceptable. And so it happens that in practice, because of these constraints, people grab normal PRNGs, normally actually PRNGs constructed for the purposes of cryptography, cut a bigger chunk of it out, throw it away, and say it will suffice because it works quickly, and we can sample from it a lot of noise, and then this is good enough because I have real-time constraints. And obviously, any sort of a guarantees that you would normally be observing out of those PRNGs, they kind of go out of the window. And that's a bit of a problem. So when we started this project, me and Ross, we had a long stream of papers looking at the intersections between systems and machine learning. We were looking explicitly for an application of a quite standard security/safety technique that is used in machine learning that actually relies quite a bit on the underlying hardware as a source of randomness. And we found one. It's called, hold and behold, randomized smoothing. So for those who are not familiar, the idea is relatively simple. It's in the limit just an uncertainty estimator. Basically, what you do is you can grab a single data point. You can then apply a little bit of noise on top of it such that it covers quite a lot of space. In the limit, obviously, you cover all of the possible space. And then you compute predictions. And then you compute basically the bounds on upper bounds and lower bounds. If we assume limited sample size, you basically can say with a certain probability how much adversarial examples will I observe, i.e. can somebody manipulate it. Importantly, it's used for both purposes, safety and security. In case of safety, this is as simple as saying, what is the confidence of my prediction? So if my car says I want to turn right, with what probability would you actually expect this to turn right with respect to the input? And then for security, it talks about robustness of the decisions with respect to adversarial examples, right? And yeah, so people actually use this in practice, more so for uncertainty estimation, and less so for adversarial robustness, although you'll find plenty of papers on the adversarial robustness side. So what do we do in the paper? In the paper, our goal is to construct PRNGs such that they pass all of the standard NIST tests. So normally you would deploy them without anything in mind, whilst at the same time properly manipulating the randomized smoothing algorithm that is running. And importantly, what we're looking for is either a way to deterministically increase or decrease the confidence in the prediction that is performed or estimating this absolute. So the best way to think about this is on the left, you have this data point and you would normally explore the space around it and estimate an absolute. Then in the right case, what you'll observe is you want to bias the noise such that your coverage is different, perhaps bigger, perhaps slower, smaller, or goes in some directions. And then ultimately you just under-approximate or over-approximate the epsilon. Super simple. Nothing much more than that. So you can imagine a very naive adversary here. First, let's imagine that you take the expected distribution and you replace it with some other distribution just to show you the worst case. Does this work? And what you'll discover is that, sorry, too many numbers. There are going to be many numbers. You'll discover that it just actually causes quite a lot of degradation in performance out of your randomized smoothing, not unexpected. So good case is when correct class is very big, and obviously you'll observe as you keep on varying different types of noise against the expected noise, you discover that it drops quite significantly, even in cases where the noise distributions are relatively similar. But at this point, you would say, Ilia, what are you talking about? Those distributions are quite different. Of course, they're not going to pass. You're going to detect this. And I agree with you. So we can do better. So I'm not sure how many of you know how floating points numbers are made and how one constructs Gaussians out of uniform noise. Because the fundamental primitive that we have with computers is to sample uniform noise, again, because of cryptography. And basically, it's one of those fundamental questions. For those of you who have seen the art of computer programming from Knuth, there is a fundamental question there. And the question is, let's construct a Gaussian out of the uniform noise. So there are many different methods, but one of the most commonly used one is the ziggurat method. And basically what this does is it numerically approximates a Gaussian. It splits this into a lot of different bins, and then it says the first couple of bits which are sampled dictate which of the bins to fall in, and the second half of your bits basically dictates where inside you want to be falling, right? But the important thing here is that not all bits are the same. Some of the bits can cause quite a significant degradation out of what exactly is going to be the shape of your distribution. In this particular paper, we'll only change 1 bit out of 64. So from the previous example, one of the first slides, this will amount to changing 3 bits inside there in the sequence. So we consider 3 particular adversaries there and 3 effects inside: the negative, positive, kurtosis, and skewness. The best way to think about this is leftmost case will sample less from the support, rightmost case will lose a little bit of volumes in the tails, and in case of skewness attacks, we'll basically lose a big proportion of the distribution. Again, a lot of numbers. Please don't look at them. It doesn't really matter. What matters inside is that if you look at the maximum degradation observed in the estimation per point, and that is the column that is highlighted in the red, is that you can cause as much degradation with the attack methods we described as with completely changing the underlying distribution. And that's an important part. That is, by single change, a single bit change introduced in the PRNG, you can cause quite a big degradation in performance. This is where you would say, okay, so, but does this translate to actually passing the randomness test, the NIST standard tests? So we run a whole bunch of, basically all of the tests, pretty much, out of the test suite. And we discovered that we do, for some of the configurations, actually fail of the tests. And actually out of, I think, 14 or 12 here, we fail 3. And here we run those tests for much larger sample sizes than actually what NIST recommends you. And if you were to look at actually how those particular tests that failed scale, you'll discover that NIST recommends at least 10 to the power of 3, and you'll notice 10 to the power of 3 are pretty much passed for them. And you only start seeing an effect once the line falls beneath the dotted line, namely for larger sample sizes. An important thing here to mention is a lot of PRNGs, a lot of constructions of pseudorandom number generators actually fail these tests at this sample size. So this is not a litmus test. It's also a probabilistic sort of a thing. At the same time, I want to mention, because in machine learning, we actually test explicitly very particular noise distributions, you can actually test for them. And the sample size complexity, because it's a parametric test, is actually going to be quite low. So here, for example, for some of the tests, 10 to the power of 2 is totally enough to actually detect stuff. And importantly, there is a lot. Funny fact, PCG64, totally normal PRNG, actually fails one of the tests here. And yeah. I guess, given the limit of time, I just want to summarize this by saying we have quite a lot of legacy technical decisions that are made because they were designed for a drastically different application. And as we start deploying machine learning where we rely on legacy systems, we may want to start revisiting some of the standards that underlie everything. I wanted to come with good news and say we've managed to introduce a change into the standard and make sure to refer to the explicit machine learning applications, but I failed. It turns out to be much harder than I thought it is to change the existing standards. Thank you very much.